Okay, again, we're on the 1709-11 document. And actually, I think it was number 2. Asked you to reason some things out symbolically from definitions. Now, I remind you of the trapezoid for V naught, VF, delta T, because I think the situation said you're given VF, V naught, and delta T. So if you're given VF, V naught, and delta T, no, actually I think you're given V naught, VF, I don't remember what you're given, doesn't matter. We look at how you reason it out no matter what you're given. Anyhow, the V naught, VF, delta T graph is going to have slope VF minus V naught over delta T, which is delta V over delta T, rise divided by run, and average velocity VF plus V naught over 2, so that the area is VF plus V naught over 2 times delta T, area being average altitude times width. And then we can write those relationships down. And I use delta S instead of delta X because that's a notation that you might often see. It's a pretty standard notation for displacement. And delta X is, of course, just displacement along the x-axis. Delta S might be a more general symbol for displacement. And it might often be a vector also. Okay, so I don't see where I've stated what was given. But yeah, okay. We assume that we're given I'll write it up here. Then we're asked to reason out delta T from the definitions. And our definitions are, well, they're up here, I'll refer to this. V bar equals delta S over delta T. That means average velocity is the displacement divided by the time interval, which is just the uniform acceleration form of the idea that the velocity is a derivative of position. Okay, velocity function is a derivative of the position function. As delta T goes to 0, this becomes this. As delta T goes to 0, this acceleration equals delta V over delta T becomes acceleration equals dV over dt. So for uniform acceleration, we have these. Again, remember this because the V versus T graph is linear, so you can use the, well, actually this doesn't matter. Because that is the definition of average velocity. Okay. Okay, well, we have these relationships. So if we know our delta S, and our V bar, we can find our delta T, right? Okay, well, if we know V naught and VF, then we know, or we can easily find average velocity V bar, and we can use this. We average the initial and final velocities, we get V bar, we've given delta S, so we're going to be able to find delta T. So we can say delta T is delta S over V bar, and then since V bar equals VF plus V naught over 2, delta T is delta S over this, simplifies to this. And we didn't have to consult the trapezoid, we didn't have to consult formulas, although we have one up here that get it for us very easily. We were able to directly reason it out based on these definitions. And the fact that acceleration is uniform, so that V bar is VF plus V naught over 2. Okay. Then we sketched a picture, okay? And I'm going to resketch the picture just to develop it. You got V naught, VF, and delta S. Those are the three given quantities. We can draw a picture of how this can be analyzed. We know from V naught and VF that we can get V bar, and we know from V naught and VF we can get delta V. And just subtract to get delta V, just average the two to get V bar, and I wrote that as a vector. Okay? Then, knowing V bar and delta V, and in addition to V naught, VF, and delta S, what can we do? Well, if we go look at the definitions, V bar is delta S over delta T, so we can put V bar together with delta S to get our delta T, right? Now, when I wrote this down, I just wrote down V bar here, delta V here. I would have been better off to put my V bar over here, close to delta S, and maybe put my delta V over here, okay? So I could have written it out the way it was, but I'd have had to have kind of looping lines connecting things. So I choose to write it like this, and I see that I can now get my delta T, and I had a line here, and I'll explain. This, and this form a triangle because we have a direct relationship between V bar, delta S, and delta T, basically this definition. Meaning that if we know any two of these quantities, we can easily solve for the third. Okay, over here, V naught, VF, and delta V. Okay, now, and I actually connected those here to indicate that we have a triangle. We don't. But we do have one here. Okay. I misplaced a line here. I want to make sure that wasn't it, make sure it's right. Okay, so we got V naught and VF and delta V. We got V naught and VF give us V bar, but okay, actually we do have a triangle up here. Just got done saying that in class. If you know delta V and V naught, you can get VF. If you know delta V and VF, you can get V naught. If you know V bar and V naught, you can get VF. If you know V bar and VF, you can get V naught. So that any two of the three quantities here, you get the third. Any two of the three quantities here, you can get the third. And this line here doesn't have a meaning yet because, of course, we don't have a triangle. Yeah, actually we do. Yeah, I just showed it. Okay. Okay. Now, having obtained delta T, what could we combine with delta T? Okay, well, if we combine delta V with delta T, well, they're both part of this definition. So that gives us A. So here's A. So that delta V and delta T can go together to give us the acceleration, just by the definition of uniform acceleration. And of course, this is a triangle. I don't know why I erased it. That was a triangle, and it still is. Okay, so we get a triangle here between delta VA and delta T, simply because if we know any two of these quantities, we can find the third. Then if we know okay, this is the line that shouldn't have been there. Because we know delta V and V bar and the acceleration, we can't directly find one of these from the other two. Now if we know delta V and V bar, we can find delta T and then put that together with the acceleration. would need to know something about displacement in order to get V bar. So we can't really do that. Okay, now the whole idea is simply that we construct this, and any triangle within this picture consists of three quantities that can be directly related to one another by simple equation, usually by multiplication or division. In this case, you're going to subtract the two. In this case, you're going to average the two. So it's not always a multiplication or division, but there's still a relationship, an equation that involves only those three quantities. So if you know two of them, you can find the third. Okay, so there's a picture. Now there are many other ways the picture could be drawn. If I know V naught, VF, and delta T, then I think, okay, well, I can get my delta V here. I can get my V bar here. I can put V bar together with delta T to get my delta S. Now I've got to put my delta T together with delta V somehow. So this is not the most convenient place to have delta T, so I kind of have to make a generalized triangle. But delta V and delta T can go together to give me the acceleration, okay? And the diagram's a little less convenient this way. If I put V naught, VF, and delta T on the line up here, it's a little harder to draw the diagram. So that's kind of a nicer diagram, but it doesn't matter. You can map out the relationships and see what's related to what, and then think about why they're related and how they're related, and work your way through the problem to understand every step. Okay? So, come back to this in a minute.